Hi, this is Larry Singyan. I'm just doing a video for my Lab 6 Experiment 2. So right now I have the Nucleo running in debugger mode, as you can see by the blinking lights. And I'm just going to talk about the setup. So first off, I have this blue wire, which is connected to port B11 of the Nucleo. And if we follow where this blue wire is going, it is connected to a resistor on the push button itself. So this blue wire is basically detecting when the state of the push button changes so that it can trigger an interrupt in the code. If we look at the push button on the other end, we do have the RC filter to filter out any debounds. Although I found that this switch doesn't have a debounce, I kept this RC filter just to be safe. And the other end of this RC filter is connected to this ground wire on the breadboard. So that's for the switch button. Moving on to the LED, this brown wire is connected to one end of the LED, as you can see. If we follow that through, it is connected to port B8 on the Nucleo board, and that port, the GPIO pin, is responsible for changing the state of the LED. And then if we look at the other end of the LED, it's connected to a resistor, the current limiting resistor, and then the other end of that current limiting resistor is connected to ground. So that's the setup. Looking at the actual functionality of this lab, you can already tell the LED by default is blinking at a rate of 2 times per second, or 2 hertz. And we can also confirm that by checking out the oscilloscope. So I have the analog input of the Atom 2000 connected to the LED pin. So if we go over to our computer and we do a single capture, so here it's capturing. We can visually confirm. We can confirm that the signal indeed is the LED is indeed blinking at twice per second. Just a quick parameter rundown. I have the oscilloscope at 500 milliseconds per division, and the volts per division is 1 volts. So as you can see, the oscilloscope has finished capturing data. So here, if we take our cursor and we measure one end of when the signal is high and the other end of when the signal is high as well, we can go and take a look at the delta t, and you can see it's at about 500 milliseconds. So for 500 milliseconds it's on, and then if we move this cursor to the next instance when it's on, when the LED is on again, so right here, if we take a look at the delta t, it's at 1 second. So within a time span of 1 second, your LED is on twice. So it's blinking at a rate of 2 hertz. So that was the default configuration. If we go and we press the push button, we can visually confirm, look, that the LED is blinking slower. It's now blinking at a rate of 1 hertz as intended. Again, we can visually confirm it, or we can also go here in our oscilloscope, do a single capture. So let's wait for a little bit, and we can easily confirm. You can already see here that it is getting bigger, that the interval when it's on, LED is on, is getting bigger, so it's slower. But we can confirm it. So if I take the cursor again at one end when the LED state transitions from low to high, and I take the other cursor when it transitions from high to low, and I check out the time interval, so it's 1 second. So this whole interval when it's on is 1 second. And then if I do take this cursor and I move it to the next instance when the LED is on, we can check out the delta t, which is approximately 2 seconds. So that means that in a span of 2 seconds, the LED has blinked twice. So that means it blinks once per second, as intended. So yeah, and that's pretty much it. We confirmed it with the oscilloscope. We've confirmed it here on the breadboard. So, and then just another quick test. It's blinking at a rate of 1 hertz. If I push the button, it's going to start blinking at a rate of 2 hertz. Again, I push the button, it's going to start blinking at a rate of 1 hertz. And I can keep doing that because it's fun. But yeah, anyways, that's it. Thank you for watching.